Welcome to our journey into group theory. Today, we are going to explore a fascinating and powerful concept called automorphisms. We will discover exactly how mathematical groups can be mapped onto themselves while perfectly preserving their internal structure. This idea is not just abstract math, it is the foundation for understanding symmetry in the universe. Before we look at the math, imagine a square table with four identical chairs. If everyone moves one seat to the right, the overall arrangement looks exactly the same. You have mapped the table to itself without breaking its structure. In mathematics, an automorphism does exactly this for groups. It is a special mapping from a group onto itself that is both a bijection, meaning no elements are left out or duplicated, and a homomorphism, meaning the internal rules of the group are perfectly preserved. Now that we understand what an automorphism is conceptually, let us look at its formal mathematical definition. The core property is that the function phi applied to the product of A and B must equal phi of A times phi of B. Conceptually, this means doing the math inside the group and then transforming the result is exactly the same as transforming the pieces first and then doing the math. The symbol phi represents our transformation function, while A and B are just any two elements chosen from our group. If this equation holds true, the structure is perfectly preserved. Before we move on, let us see this with a concrete example. We want to find all automorphisms for the group of integers modulo 4 under addition. The elements are 0, 1, 2, and 3. A key rule is that automorphisms must map generators to generators. Here, the generators are 1 and 3. So the element 1 can only map to 1 or 3. Let us test our first candidate, assuming phi maps 1 to 1. To see what happens to the number 2, we write it as 1 plus 1 and split the function. Continuing with our first candidate, we substitute the known value of 1. 1 plus 1 equals 2, so 2 maps to 2. Following this logic, 3 maps to 3. This candidate is simply the trivial identity mapping. Now let us test the second candidate, where the generator 1 maps to the other generator 3. This will shuffle the elements. We again evaluate the number 2 by breaking it down into 1 plus 1 and splitting the function across the addition sign. We substitute the value 3 for each function term. 3 plus 3 gives us 6. But remember, we are in modulo 4 arithmetic, so we divide by 4 and keep the remainder, which is 2. Thus, 2 maps to itself. Finally, we evaluate 3 by adding 3 ones, giving us 9, which leaves a remainder of 1. We have successfully mapped every element. This gives us a final answer. The group has exactly 2 automorphisms, the identity mapping and this new mapping that multiplies everything by 3. Let us look at a visual representation of the transformation we just calculated. On the screen, you see 2 sets representing a group of integers modulo 4. The arrows show exactly where each element is sent by our second automorphism. 0 stays at 0 and 2 stays at 2. However, 1 and 3 swap places. Notice that every element on the left has exactly one arrow pointing away, and every element on the right has exactly one arrow pointing towards it. This visually confirms that our mapping is a perfect bijection. Now that we have seen a finite group, let us determine the automorphisms of the infinite group of integers under standard addition. This group never ends, but it is cyclic, meaning it is generated by a single element. The generators are 1 and negative 1. Since generators must map to generators, let us explore the case where 1 maps to negative 1. To find a general formula for any positive integer n, we write n as a sum of ones and apply our function. Because our function is an automorphism, it perfectly preserves addition. This means we can split the single large function into many smaller functions added together. We substitute the value -1 for every single function term in our long sum. Adding -1 to itself n times simply gives us -n. This shows that our mapping is the negation function. Since the only other option was the identity function, we conclude that the infinite group of integers has exactly two automorphisms. We have successfully found automorphisms for specific groups. This brings us to a very important theorem in group theory. The set of all possible automorphisms of a group actually forms a group itself under the operation of function composition. To prove this is true, we must show that this set satisfies the four group axioms. The most critical step is proving the closure property, which means that if we compose two automorphisms, the resulting combined function is still a valid automorphism. Let us prove this closure property step by step. We start by taking two valid automorphisms, which we will call alpha and beta. We need to show that applying one function after the other still perfectly respects the mathematical rules of the group. We begin by applying the definition of function composition to the product of two group elements, A and B. The small circle symbol represents composing the two functions. This means we first apply the inner function, beta, to the combined product of our two elements. This sets up our equation so we can use the special properties of these functions. Now we focus on the inner function beta, which is applied to the product. Because beta is an automorphism, it is guaranteed to preserve the group operation perfectly. So we can split it into beta of A times beta of B. Next, we apply the exact same logic to the outer function, alpha. Since alpha is also an automorphism, it splits across the new product just like the inner one did. Rewriting this in standard composition notation, we see that the composed function preserves the group operation. This proves the closure property, confirming the set of automorphisms forms a valid group. So, we have proven that automorphisms form their own groups. But why does this matter in the real world? In physics and chemistry, automorphisms are the rigorous way to study the hidden symmetries of a system, like a crystal lattice or a complex molecule. In computer science, they are absolutely crucial for modern cryptography. The security of many encryption algorithms relies on the unpredictable properties of automorphism groups. By understanding how a structure maps to itself, scientists can predict properties that will not change even under massive transformations. Let us review what we have learned today. An automorphism is simply an isomorphism from a group to itself. It acts as a structural shuffle, rearranging the elements without changing the underlying rules of how they combine. We also saw that the set of all automorphisms forms its own group under function composition. By studying these mappings, we gain deep insights into the internal architecture of mathematical systems. You now understand the core concept that forms the bridge between abstract algebra and the real-world study of symmetry.